Hi there, welcome to N6.6 Integers. So N6.6 says we're demonstrating an understanding of integers concretely, that means with blocks or something, pictorially and symbolically. So pictorially is a picture, symbolically is with actual numbers. So first one, explore and explain the representation and meaning of negative quantities in First Nations and Métis people past and present. So this one we're going to rely on our elder, Armin MacArthur, is going to come out and have a bit of a discussion with us about that one, so we won't talk much about the video. There's also a poster in the back of my classroom that you can have a look at how First Nations and Métis people represent quantity. So have a look at that one. Second indicator here says observe and describe examples of integers relevant to self. So the biggest one is going to be temperature, especially for us living in Saskatchewan. We always talk about negative temperatures because we have them probably 80% of the year. So temperature. Compare two integers and describe their relationship symbolically using less than, greater than, or equal to. Now, here's how you remember less than, greater than, and equal to. The less than sign, this guy, kind of looks like a crooked L. See that? So when you're writing with those signs, you can say 56 is less than 100, right? Because that sign kind of looks like an L. Okay. So just as if you were reading it in English, you would say 56 is less than 100. You're just reading it from left to right. Okay, the other way to remember that is this is an alligator. And he always eats the biggest number. So he would totally eat 100 because that's the biggest number. So you can remember it two different ways, that less than looks like an L, or the alligator always eats the biggest number. All right, moving on. Next indicator says represent integers concretely, pictorially, or physically. So very similar to what we said up top. Put a set of integers in order, greatest to least, or decreasing order, whatever they ask for. Identify and correct errors when you're putting them in order. Extend a number line by adding more numbers. So a number line, when we were little, we used to think that a number line started at 0 and it just got bigger and bigger and bigger to like a bajillion, right? But now we know, because we live in Saskatchewan, we could have a temperature of 0, we could have a temperature of 10, we could have a temperature of -10, and so on and so on and so on. So if we said extend the number line to the left, you could say, well, it's going to get down to -60 eventually, right? Or extend the number line to the right, it's going to get up to +60. So number lines can go both ways. Explain the role of 0 with integers and how it is different from other integers. So 0 is kind of that middle ground. It is neither positive or negative. It is right in the middle. It represents no quantity. It's just 0. Did you know that back in the early Greek days, when they were working with numbers like Pythagoras and those cool dudes back then, they actually didn't have 0. 0 wasn't really invented until later on in math. So it would have been very difficult to do math without a 0, I think. So they must have been pretty smart. All right. Again, I said look on that back poster, but you'll see that First Nation and Métis mathematics, they used math all the time for measuring. So it could have been measuring quantities for what they're cooking, could have been measuring a animal hide for how to make a teepee, so tons of measurements that they would have had to do all the time. Locating different objects if they were trying to find other communities or perhaps the animal that they were hunting, they would give directions to each other and tell them how many paces or whatever the measurement unit of the day was. So they would use it for maps. Playing, so math was actually a part of a lot of different games that our First Nation and Métis people had. And we've got some examples on the back wall, but keeping score, something as simple as, oh, I get a point, you get a point, I get 2 more points and 3 more points, and I have 5 points and I win. So things like that. Same with counting, keeping track of stuff up there. Designing, so if you're making clothing and you need to know someone's measurements of how big to make it, how big to make your village, because your teepee is going to take up a certain amount of space, so lots of calculations that went into planning a village. And explaining things. One of the phenomenon that First Nation had to explain was, say, cycles of the moon or the tide or weather or how many days it had been since a certain thing happened. So they used math all the time in those explanations. Okay, so here's a few number lines. Let's look at the very top one. It says that negative numbers are going to the left of 0 and positive numbers are going to the right. Now, something interesting that I've noticed with some of my students, one of the misconceptions is that they will draw a number line and go 0, 1, 2, 3, 4, etc., etc. They got that part right. And then when they go to make the negative side, going to the left, they'll start at some wacky number like 10 and either go backward 9, 8, I don't know what they're doing. These numbers are basically a mirror of those numbers. So this wouldn't be right at all. You'd have to start at -1, -2, -3, etc. So once you get to 0, it's kind of like starting from scratch again, except you're going the opposite direction. Okay, so some integers in the real world situations. Here's a couple of examples. A jet climbing to an altitude of 20,000 feet. So they've given that a plus 20,000. So if you have a jet and it's at 20,000 feet flying along and it loses 5,000 feet, well, 20,000, take away 5,000, he is now at 15,000 feet. This example sounds more like Mrs. Carver taking $15 out of the bank, and your bank account then shows you have a -15. So banking is another common example of where we use integers, especially if you're my bank account, you always see a negative sign in front of your account balance. So sad. Okay, on to the next one. How do we compare and order integers? So the numbers are getting smaller as we go to the left. The numbers are getting bigger as we go to the right. Who's in the middle? 0. So they're saying, would you rather have $2 or -$2? Well, obviously, we would rather have $2 because that means it's positive. If we had -$2, that means we owe somebody $2. Okay, so extending the number line, what do you think would go, I'm going to change color here so you can see it. What do you think would go right here? So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What comes after 10? I hope you said 11. What would come next? I hope you said 12. And you could carry that number line on forever and ever. So on the red side, the negative numbers, what would come right here after -10? If you look at the pattern, you've got -1, -2, -3, so on, so on, so on. So I hope you said that the next number is going to be -11. All right, here's our example of temperature. If you live in Saskatchewan, you should get a thermometer that looks like this round one. And here's why. You'll notice it has numbers on the inside of the screen, the little numbers inside there. There's the 60 or the -60, and then it has big numbers on the outside. Why do you think it has 2 sets of numbers? Well, this one is sort of hidden, but you can see in behind this red thing, it has a F, and that means Fahrenheit. Now, Fahrenheit, Canadians used to use the Fahrenheit scale, But a few years ago, we switched over to the metric system, and so now we use Celsius, and that's why you see a C right there. So Celsius. So most of the time, thermostats and thermometers show both measuring systems, and you can see how they compare. So this round thermometer is at 0 degrees Celsius. The red pointy thing is pointing to the 0, which is on the outside row. So those are the Celsius numbers. And the reason that they chose 0 to be the middle point here or whatever, it happens at 32 degrees Fahrenheit. So you can see here's 20, here's 40, right there would be 32. So 32 degrees Fahrenheit is exactly the same as 0 degrees Celsius. This happens to be the freezing point of water. And they thought that was kind of an important benchmark. That was an event that everybody sort of understood that water freezes at that specific temperature. So when they made the Celsius thermometer or thermostat, they decided that 0 degrees should be at this important point, freezing point, something that everybody knew. Whereas on the Fahrenheit scale, 32 degrees is kind of a random number to have such an important event as the freezing of water. So it makes more sense for Canadians to use the Celsius because we know all about the freezing point of water. So the other reason that Canadians should have one of these round gauges, temperature gauges, is because the round ones often go, you can see the coldest temperature on here is minus 50 Celsius. That's pretty cold. It really doesn't get much colder than that. You might hit minus 55 or minus 60 every couple of years. We might have a day like that in Saskatchewan, but really minus 50 is about as cold as it's going to get. And you'll notice on these bar thermometers, they don't usually go that cold. This one only goes to minus 40. Now you can see that the two scales, on this side is Fahrenheit and on this side is Celsius, but minus 40 is exactly the same spot. So that's just an interesting point that minus 40 is actually the same temperature on both scales. That's sort of where they meet up. Okay, so to remember that 0 is 32 degrees Celsius, you need to look up the song. I'm not sure who it's by, maybe Alan Jackson. It's called The Drinkin' Bone. And now I'm going to subject you to it. So he says, the drinking bone's connected to the party bone. The party bone's connected to the staying up all night long. So that's the song. There is a line in the song that says, 2 plus 2 is always 4. Down is south and up is north. And 32 degrees is freezing cold. So remember that 32 degrees is freezing cold. And there's my solo for the day.